Hi, everyone, and welcome to week 15 of Introduction to Logic. This week, we're going to be looking at identity statements in predicate logic. Now, if you remember, in predicate logic, lowercase letters a through w are constants that refer to a particular object. Each constant, a through w, can stand for or refer to only one particular object. But for any given object, more than one name can refer to that object. So in this case, lowercase constant a and lowercase constant b can both refer to the same object, but it's very important that the letters a through b refer to one and only one object each. Let's look now at a simple identity statement in English. Let's take the statement Batman is identical to Bruce Wayne. Let's let the lowercase constant b stand for Batman. Let's let the lowercase constant w stand for Bruce Wayne. And if you want to say that Batman is identical to Bruce Wayne, you just write B equal sign W. And the equal sign in predicate logic is used to mean identity in the sense that two objects are identical to each other. So in this case, the lowercase constant b is a name that refers to Batman. The lowercase constant W is a constant that refers to Bruce Wayne. And saying B is identical to W tells you that both of those names, B and W, refer to the very same person, the person who is both Batman and Bruce Wayne. In predicate logic, we also have non-identity statements. So consider this example. Batman is not identical to Clark Kent. Let's let the lowercase constant b stand for Batman once again. Let's let the lowercase constant c refer to Clark Kent. And there are two ways that you can translate this. Non-identity is translated using the what looks like an equal sign, but in logic it's an identity sign with a hash mark through it. So here we have b is not identical to c right here. You can see lowercase b is not identical to the constant c. And we can also translate it this way. We can also say it's not the case that B is identical to C. So if you just had B is identical to C, you could put parentheses around that and put a tilde or a negation sign in front of that to indicate it's not the case that B and C are identical to each other. Either one would be just fine. Your textbook tends to use this identity sign with a slash through it for non-identity, but you could also use this negation in front of an identity sign right here in translation 2. Either of these would be equivalent to each other. They both say that the object referred to by B, Batman, is not identical to the object referred to by C, or Clark Kent. In other words, those are two different individuals or two different objects. So identity statements let you translate various kinds of statements in English into predicate logic notation that you wouldn't be able to translate otherwise. And hence, ultimately, you'll be able to do proofs using identity statements inside the proofs as well. We're going to get to that by the end of the video. One type of statement that you can translate using identity statements are what are known as only or the only statements. And these are two different types of statements. Only statements are different from the only statements. And before I dive in, this is going to be a little tedious because there are so many different types of statements in English that sound very similar to each other, but really have very different logical semantics. So there is really going to be no purely mechanical way of translating from the English into the logical notation. What is important is that you capture all the semantics or all the meaning of these different types of individual statements. Hopefully, running through some of these examples will help you clarify the distinction between some of these different phrases in English. Ultimately, hopefully, having learned about the logical semantics of these different constructions in English, you'll improve your use of grammar in this regard. That when you're choosing your words and in these types of statements, you'll choose your words a little more carefully to make sure you're saying exactly what you mean to say when using these kinds of statements. Let's look at a very simple example. At the top of the screen, you see a statement, only Batman drives the Batmobile. So here we're going to let lowercase constant b stand for Batman once again, and we're going to take the one place predicate dx and let that stand for x drives the Batmobile. This statement is saying two things. It's saying, first of all, that Batman does drive the Batmobile. And you can see that here in the first part of the sentence. DB, capital letter D and lowercase letter b, says that the predicate D is attached to the object B. In other words, Batman drives the Batmobile. But that's not all this English sentence says. It says that only Batman drives the Batmobile. So we need a way of indicating that there's no other person or object that drives the Batmobile besides Batman. And that's what's happening in the right-hand conjunct of this statement. The right-hand conjunct says, for all x, in other words, for anything in the universe, if that x drives the Batmobile, then that x is identical to Batman. Let me read this entire statement to you in logic speak, And I think you'll see why this logic notation is equivalent to the English language statement given above. So from left to right, this basically says Batman drives the Batmobile. And for all X, in other words, for anything in the universe, if that X drives the Batmobile, then that X is just identical to Batman. In other words, anything at all that drives the Batmobile has to be identical to Batman. And that's a way of saying that only Batman drives the Batmobile and that Batman does indeed drive the Batmobile. That's what's given in the first part of this statement. So by contrast, let's look at the next example, what's known as a the only statement in English. And again, this is slightly different than the example given above, and I think you'll see why. So this statement says the only car driven by Batman is the Batmobile. So we have a couple of given predicates and objects here. Lowercase letter b is going to stand for the Batmobile, not Batman, but the Batmobile in this case. Let's let the one place predicate dx stand for x is driven by Batman. I could have used a two place predicate there, something like dxy, where x drives y, but that's a little extraneous for this case, so I just used a one place predicate there. And cx, we'll let that stand for x is a car. So in order to convey all of the information in the given statement, the only car driven by Batman is the Batmobile, we need to say a few things. We need to say, first of all, the Batmobile is a car. Next, we need to say it's driven by Batman. And then we need to say it's the only car driven by Batman. So we basically say this, for all x, if x is a car and driven by Batman, that's what's happening in the antecedent of this conditional governed by the universal quantifier. So in other words, for anything that's a car and driven by Batman, if there's only one car driven by Batman, everything that's a car and driven by Batman has to be identical to the Batmobile. And that's what's going on here. So for in the consequent of this conditional. So inside this universal quantifier, we have take anything you want that's a car and driven by Batman, then that object X is identical to B, the Batmobile. Next, let's look at what are known as no except statements. Now, your textbook provides different classifications of these statements, and I've tried to break them down the same way that your textbook has for clarity and to make it easier to match up with what you're seeing in the textbook and what you're seeing in the slide presentation. I'm not really happy with the name no except statements. It's kind of a clunky phrase in English, but here's an example of one. No starship except the Enterprise is commanded by Captain Kirk. Let's let lowercase constant e stand for the Enterprise because that's just an object. Let's let SX, the one place predicate, stand for X is a starship. And let's let CX stand for X is commanded by Captain Kirk. So we need to say a few things here. First of all, we need to say that the Enterprise is a starship. That's what's happening in this first conjunct, SE, that I'm highlighting right now. We also need to say that the Enterprise is commanded by Captain Kirk. That's what's happening in the second conjunct. Now, what's happening with this long universally quantified statement here, the right-hand conjunct of this string of conjuncts? It says for all X, if that X is a starship and commanded by Captain Kirk, then that X is identical to the Enterprise. And this is a way of saying that there aren't any other starships that are commanded by Captain Kirk except the Enterprise. Basically says take anything you want, anything in the universe. If it's a starship and it's commanded by Captain Kirk, then it has to be identical to E or identical to the Enterprise. So this serves to say there's only one starship commanded by Captain Kirk, that there aren't any other starships commanded by Captain Kirk beside the Enterprise. Next, let's look at what are known as all except statements. Here's an example of one. All Klingons except Lieutenant Worf are mean. Lieutenant Worf being a character from Star Trek The Next Generation. I'm a Star Trek fan, so I keep using Star Trek examples. Let's let the lowercase constant W stand for Lieutenant Worf. Let's let the one place predicate KX stand for X is a Klingon. And let's let the one place predicate MX stand for X is mean. So in order to caption the semantics of the given statement, the meaning of the given statement, we need to say a few things. First of all, we need to say that Worf is a Klingon. That's what's going on here in the first conjunct, KW. We also need to say that Lieutenant Worf is not mean. The given statement implies or connotes that Worf is not mean. So that's what's going on here, not MW. It says Lieutenant Worf is not mean. Now we need to say that all other Klingons that are not Lieutenant Worf actually are mean. So that's what's going on in this long, universally quantified conjunct on the right hand of this string of logic notation. It says for all X, if that X is a Klingon but not identical to Worf, you see there's a negation of an identity statement here. says take anything you want. If it's a Klingon, but it's not identical to Worf, in other words, all Klingons except for Lieutenant Worf, then that X, those Klingons are mean. That's what's going on in the consequent of the conditional bound by that universal quantifier. So reading it from left to right, it says Worf is a Klingon, Worf is not mean, and any Klingons that are not identical to Worf are mean. That's what's going on in the universally quantified statement on the right hand of that string of logic notation. So that's how you do an all except statement. Next, we have superlatives, and superlatives are statements where something is the highest, the best, the brightest, the most, the maximum quantity of a particular quality or a particular property. So here's a given example of a superlative. Sirius A is the brightest star in the sky. That's the superlative. It's the brightest. So let's let the lowercase constant s stand for Sirius A. Let's let the one-place predicate sx stand for x is a star. Let's let the two-place predicate bxy stand for x is brighter than y. So let's look at this string of logic notation down below and see how it matches up with the semantics or the meaning of that given statement. First of all, we need to say that Sirius A is a star. That's what's going on here in the left-hand conjunct, SS. Capital letter S being the predicate is a star, and the lowercase letter s standing for Sirius A. So Sirius A is a star. Then we need to say that for all the other stars that are not equivalent to Sirius A, that S, in other words, Sirius A is brighter than all those other stars. So we need a way of defining a group for all of the stars that are not equivalent to Sirius A, all the stars except for Sirius A. So we're going to need a universal quantifier. And we said that the antecedent of the conditional inside that universal quantifier is going to be the group that we're talking about. So here we're talking about, first of all, things that are stars and things that are not identical to Sirius A. That's why we have the non-identity statement inside the antecedent of this conditional. And then the right hand, in other words, the consequent of that conditional is going to be what we're saying about that group. And we're saying that Sirius A is brighter than everything other than Sirius A. So we have the predicate B, brighter. And again, the first slot here, the first constant refers to Sirius A. So Sirius A is brighter than X. In other words, Sirius A is brighter than everything we've defined here, which is stars that are not identical to Sirius A. So this is how you handle superlatives. But again, it hinges on being able to define not just the object that we're talking about, but a group that excludes the one object that we're talking about. And that's what's going on here, stars that are not identical to Sirius A. There are also various types of numerical statements in English. For example, here are some statements known as at most statements. So here's a given statement. There is at most one captain of the Enterprise. So let's let the one place predicate CX stand for X is captain of the Enterprise. This is going to look a little strange because we're talking about there being at most one captain of the Enterprise. And the way you do this in logic is with two universal quantifiers. It says for all X and for all Y, in other words, for any two X's and any two Y's, if X is a captain of the Enterprise and Y is captain of the Enterprise, then X and Y have to be identical to each other. In other words, if there's more than one captain of the Enterprise, they have to be identical to each other, which is a way of saying there is at most one captain of the Enterprise, because the second you get more than one captain of the Enterprise, it's just identical to the first captain of the Enterprise. Now, it doesn't say that there actually are any captains of the Enterprise here. Notice we don't have a statement like Captain Kirk is captain of the Enterprise or there exists some captain of the Enterprise. This statement doesn't say that. It just says there's at most one captain of the Enterprise, but it doesn't actually say that there are any captains of the Enterprise, which is why we don't have an existential quantifier there. Same thing with the next example, though this one says there's at most two of something. There are at most two supervillains. So let's let the one place predicate SX stand for X is a supervillain. And I think you can see what's going on here. Basically says if there are, take any three things you want, X, Y, and Z, for all X, for all Y, and for all Z. If they're all supervillains, X is a supervillain, Y is a supervillain, and Z is a supervillain, then at least two of them have to be identical. Either X has to be identical to Y, or X has to be identical to Z, or Y has to be identical to Z. In other words, if there's more than two, if there are three of them, then at least two of them have to be identical. And that's what keeps the number to there being at most two supervillains. But again here, this statement doesn't say there actually are any supervillains. There are no existential statements here, only a statement that says if there are any, then at least two of them have to be identical to each other in order to keep the number being at most two of them. So that's how you translate at most statements in logic. Let's look at statements like this: at least a number of something, which says something very different. If you look at the given statement, there's at least one Greek poet. We have two predicates here. G of x stands for x is Greek. P of x stands for x is a poet. And this is going to look like a very run-of-the-mill, straightforward existential statement. It says there exists at least one thing that is Greek and a poet. This is just a run-of-the-mill existential statement. There's something that's a Greek and it's a poet. The next example says there are at least two Greek poets. Now, what's interesting about at least statements compared to the previous slide about at most statements is that this statement here does commit you to the existence of something. The second statement on the screen, there are at least two Greek poets, say there have to exist at least two things. They're both Greek poets. So there exists something, some X, there exists some Y down here, such that what? X has to be Greek and Y has to be Greek. X has to be a poet and Y has to be a poet. And X is not identical to Y. This non-identity clause, X is not identical to Y, is what guarantees that we have two different Greek poets, that X and Y don't refer to the same object, they refer to two different objects. So you have to have that. Otherwise, the statement as it is would just say that there exists some X, there exists some Y, and they might actually be the same object. We don't know. But once we know X is not identical to Y, we know for sure that there have to be at least two Greek poets. I think you can guess what the next slide is going to be. We've talked about at most statements, we've talked about at least statements, but what if we have an exact number of objects? So that's what we have here in this first statement. There's exactly one currently serving president of the United States. We're going to need a couple of predicates. We're going to need something like CX, X is currently serving, and let's let PX stand for X is president of the United States. This statement does commit us to the existence of something. It says there exists something that is currently serving and the president. That's what says there is actually a currently serving president. Now we need a way of saying there's only one serving president of the United States. And that's what's going on. Still inside the scope of the existential quantifier, we have this universal quantifier for all Y. If that Y is currently serving and the president, in other words, take anything in the universe that you want. If that object is currently serving and it's president of the United States, that Y has to be identical to X, that one existing currently serving president of the United States. So again, this starts out sounding like a straightforward existential statement. There exists something that is currently serving and it's president of the United States. Now we need a way of saying there aren't any more of them. So take anything you want that's currently serving and president, that object has to be identical to the one currently serving president of the United States. That's what's going on in this identity statement inside that universal quantifier. Here's another example that's a little more complicated. There are exactly two living former members of the Beatles. So we've got a couple of predicates. LX stands for X is living. BX stands for X is a former member of the Beatles. And we've got a fairly lengthy string of logic notation that I'm going to break down for you here. This sentence commits us to the fact that there are two living former members of the Beatles. So there exists some X, so there exists some Y, such that X is living and a former member of the Beatles, and Y is living and a former member of the Beatles. Now we need a way of saying there are only two. So that's what's going on here inside this universally quantified statement. Again, still inside the scope of these existential quantifiers. This says, for all Z, again, we have to use a different variable. We've already used X, we've already used Y, so we have to use a different variable. For all Z, if that Z is living and it's a former member of the Beatles, then either that Z has to be identical to X or that Z has to be identical to Y. That's what restricts the claim to talking about there being only two living former members of the Beatles. In other words, if there were more, they have to be identical to one or the other that are living and exist. One of the first two objects we defined were the existential quantifiers at the beginning of the statement. So you can see that these statements in predicate logic with identity get quite lengthy. This statement in English is not terribly complicated. There are exactly two living former members of the Beatles, but look at this very lengthy string of logical notation it takes to capture all the meaning of that one fairly innocuous looking statement in English. Your textbook also covers definite descriptions, and definite descriptions in English are descriptions of a particular person, a particular object, a particular thing, where it's not, that person isn't named by name or that object isn't described by name, but it's given a type of description. So look at this first example. The author of Romeo and Juliet was an Englishman. The subject of this sentence is the author of Romeo and Juliet, which is a description. It doesn't name the person by name. It's a description of the person. And that's why this category of statements is called definite descriptions. You're talking about the one and only author of Romeo and Juliet was an Englishman, where that subject is actually a description. So we're going to need a few things to translate this. We're going to need a predicate, lowercase r, to stand for the play Romeo and Juliet. We're going to need this one place predicate, EX, which stands for X is English, in other words, an Englishman. And we're going to need this two place predicate, AXY. X is the author of Y. It could be something like WXY, X wrote Y, but I've used AXY, X is the author of Y. So let's look now at this string of logic notation for this first example. It says there exists some X, there exists some object, in other words, such that X wrote R. X is the author of R. In other words, X wrote Romeo and Juliet. We next need to say that there's only one of them, that there weren't two authors of Romeo and Juliet. That's what's going on here in this universally quantified statement, again, still inside the scope of this existential quantifier. It says for all y, if that y wrote Romeo and Juliet, then y is just identical to x. In other words, there's only one object, and if there's more authors of Romeo and Juliet, they're just identical to the first one. That's what says there's literally one and only one author of Romeo and Juliet. And now finally, we need to say what we're claiming about that person, which is that they're English. So we have this predicate EX, X is English. So in addition to the fact that there's an author of Romeo and Juliet, there's only one author of Romeo and Juliet, and that X, that object we defined with this existential quantifier, is English. That's what's going on in the right-hand conjunct inside that existential statement. Let's look at the next example. The author, a little more complicated, the same idea, but a little more complicated. The author of Romeo and Juliet, so we have the same description. What are we saying about that person now is either William Shakespeare or Francis Bacon. So we're going to need to define a few terms here. We have the lowercase constant r, which will stand for the play Romeo and Juliet. Let's let the lowercase constant s stand for William Shakespeare. Let's let the lowercase constant b stand for Francis Bacon. And let's let this two place predicate, again, AXY, stand for X is the author of Y. So let me read this string of logic notation to you in logic speak. Hopefully the syntax and the way of pronouncing predicate logic statements is coming along more naturally to you guys after having looked at predicate logic for a few weeks. But let me talk you through this. There exists some object, some X, such that that object X is the author of Romeo and Juliet. So first of all, there exists at least one author of Romeo and Juliet so far. Now we need to say there's only one author of Romeo and Juliet. So for anything else that wrote Romeo and Juliet, in other words, for anything at all that wrote Romeo and Juliet, that Y is just identical to X. In other words, identical to the one object. That's what says there's only one and only one author of Romeo and Juliet. Now we need to say what we're claiming about that object. Well, we're saying one of two things. It's either identical to William Shakespeare or it's identical to Francis Bacon. And that's what's going on here in the right-hand conjunct inside this string of logic notation governed by this existential quantifier. That X, this object that exists, is either identical to S, which is William Shakespeare, or it's identical to B, which is Francis Bacon. So these aren't too bad. You just have to make sure you're capturing all three of these components. You need to say there exists something that wrote Romeo and Juliet. Anything at all that wrote Romeo and Juliet is just identical to the first thing. That's what's going on here inside the second part of this statement, this universally quantified section. And finally, you say what you're claiming about that object. In this case, it's a disjunction. That object X is either identical to S or it's identical to B. And this is going to vary based on what you're saying. There's no possible way I can exhaust all the possible constructions you could have, but all definite descriptions are going to have this pattern. There exists something that has the property in question. There's only one thing that has that property in question. And then finally, what you're claiming about that object. So your textbook gives you plenty of examples of all of these different kinds of statements. I want you to go slowly through this video, rewind and pause if you need to, and make sure you can understand the syntax of the logic notation and how that matches up with the given statements. Look at all of the examples inside the textbook chapter. And unfortunately, like I said, there's no possible way of doing this mechanically. You have to be able to rely on your understanding of English as an English speaker and capture the semantics or all the aspects of the meaning of the given statements in the translations. And you're going to do a lot of translations for your exercises this week. And again, this is going to be one of the hardest things you've had to do all semester because there's no mechanical way of doing them. But do pay close attention to the given examples inside the textbook chapter, and the difficulty will kind of ramp up in the course of doing the translations that you have in this section of your textbook. Now we're going to shift gears a little bit and look at predicate logic natural deduction using identity statements. As you can guess, there's a new natural deduction rule. This is the very last natural deduction rule that you're going to learn this semester. It's called the identity rule. What's a little tricky about the identity rule is that there are 3 different versions of it, and it's used in 3 different ways. You know, the textbook author might have given these 3 rules 3 different names, but he lumped them all together and called them identity. And here are the 3 versions of this rule. The first version of the identity rule, what I've called version 1, allows you to introduce a self-identity statement. By self-identity, I mean some object being identical to itself. X is identical to X, A is identical to A, B is identical to B, so on and so forth. You can introduce a self-identity statement anywhere you want inside a proof, and it doesn't matter what your premises are. That's what's going on here in the given form of this rule. From any premises you want, you can always introduce a statement like X is identical to X, or A is identical to A, or B is identical to B. And you don't have to cite any premises. You just cite this as identity. And obviously this makes sense. This is a tautology, a self-evident statement. Some object is always identical to itself, so it doesn't depend on any premises that you have, which means you can introduce a self-identity anytime you want in the context of a proof. Now, version 2 says this: if X is identical to Y, that's equivalent to Y is identical to X. So this is an equivalence rule. It says you can reverse the order of an identity statement anytime you want in the context of a proof, even as part of a larger statement, because this is a rule of equivalence or a rule of replacement. It says if you have X is identical to Y over here on the left, then Y is identical to X over here on the right, and vice versa. It goes both ways. If you have Y is identical to X, you can reverse the order of that to X is identical to Y. That's the second version of the identity rule. Now, the third version of the identity rule says this: if you have any formula at all that has an X in it, and if you know that X is identical to Y, then you can rewrite that formula using Y instead of X. That's what's going on here in the conclusion of this. So if you have a formula that has the constant A in it, for example, and if you know that A is identical to B, then you can rewrite that entire formula using B instead. That's what's going on here in the conclusion. So that's version 3 of the identity rule. Now, I want to look at just a couple of sample proofs using all of these rules together, because I don't think these rules are terribly difficult. I think you can look at just a couple of examples and see what's going on with the identity rule. Here's an example from your textbook. The first premise is FE, in other words, the predicate F. In fact, right here, I'll highlight it. The predicate F is attached to the object E. In other words, the object E has the predicate F, whatever it is. And for all X, if X is an F, then X is identical to E. You can see the identity statement as part of that universal statement that I've highlighted in blue there. The second premise says that E is not identical to N. So in other words, the E refers to one object and N refers to a different object, and E and N don't refer to the same object. Premise 3 is just Cn. In other words, the object N has the predicate C, and we're trying to prove this conclusion. There exists some X such that X is a C and X is not an F. I've completed the proof for you here. We're just going to walk through this proof step by step. In the first line of this proof, community step has been done to get that universal statement on the left side of that conjunction so we can simplify it, which is what's been done here on line 5. We've just dropped the FE and simplified the left hand of that conjunct, which is that universally quantified statement, to get it on its own line. So for all X, if F of X, then X is identical to E. Line 6 is just an instantiation of that statement. So notice that we already have the constant E inside the universally quantified statement in line 5, inside this identity statement. Because the given premises already make use of the lowercase constant n, I'm going to instantiate line 5 using the lowercase constant n. And on line 6, that will give me fn, if fn, then n is identical to e. All I've done is drop the universal quantifier and I've replaced the x with an n. That's how I got what you see on line 6. Way back on line 2, we saw that e is not identical to n. So we can reverse the order of that using the identity rule, the second version of the identity rule, to say that n is not identical to e. That's how we got line 7. Now, I want you to take a look at the relationship between line 6 and line 7. Line 7 says n is not identical to e. But the consequent of the conditional in line 6 is that n is identical to e. So because we have the negation of that consequent, we know that the negation of the antecedent has to be true according to modus tollens, which is one of the rules you should have down pat by now. So on line 8, we know that the antecedent fn has to be false or not fn. And that comes from lines 6 and 7 by modus tollens. So if that's not clear, take a look at the relationship between line 6 and 7. Line 7 is the negation of the antecedent of line 6. So line 6 says if fn, then n is identical to e, but line 7 says n is not identical to e. That's the negation of that consequent. Line 9 just conjoins line 3 and 8 together, 3 being Cn and line 8 being not f of n. And we did that so we could generalize and obtain the conclusion, which is what we have on line 10. If we know on line 9 Cn and not Fn, that means there has to exist at least one object that is a C but not an F, according to existential generalization. And that's the conclusion we were trying to prove, so we are done. There's only one other proof I want to look at for this video, and it's this proof here. Again, it's also from your textbook, but I want to walk through it with you line by line to see how it works and how the identity rule functions inside this proof. We're given three premises. Line 1 says PS and IS and this universally quantified statement for all x. If px and ix, then x is identical to s. So it's a fairly lengthy string of conjunctions there, two kind of simple conjuncts in this one universally quantified statement as a unit on the right. Line 2 is just PC and LC. Again, just to drive the point home about the meaning of it, that says that the object referred to by the constant C, it is a P and it's an L. Line 3 says there exists an object, some x, such that x is a P, x is an I, but x is not an L. So there exists something that is a P, it is an I, but it's not an L. And we're trying to prove this conclusion. C is not identical to S. Because that conclusion is negatively phrased, C is not identical to S, I'm going to try to prove this by indirect proof, which is what I've done here on line 4. Line 4 says that C is identical to S, and I've assumed that inside the scope of this vertical indented sequence. Again, this is how indirect proof works. If you're trying to prove that C is not identical to S, you assume that C and S are identical to each other, and then you try to show that that leads to an explicit contradiction, which is what I've got down here, way down here on line 18. You can see that leads to the consequence that C is an L and C is not an L, which is a contradiction, an explicit contradiction, some statement and its negation conjoined together. And if you can show that that assumption leads to a contradiction, you will have shown that that assumption has to be false, which is the conclusion. C is not identical to S. So let's go through this line by line. Line 4 is just an assumption for indirect proof. That's why I've cited it AIP, that C is identical to S, which is the opposite of the conclusion. Line 5 is an existential instantiation of line 3, which is a statement bound by an existential quantifier. And again, whenever you're using existential instantiation, you have to use a new constant that doesn't already appear in the proof, even in the conclusion line. So this proof already contains the lowercase constant c. It already contains the lowercase constant s. So we need to use a new constant a through w that doesn't already appear in the proof. And here it's been done with the lowercase constant a. So we have PA and IA and not LA. In other words, that object referred to in the existential quantified statement in line 3, we're giving it a name. We're calling it A. Line 6 is just a commutativity step to get that universally quantified statement on the left side of that string of conjuncts so it can be simplified. That's what's going on here in line 6 and 7. Line 6 is just a rewriting of line 1, reversing the order of it. And line 7 simplifies out that universally quantified statement on its own line. Next, that statement is going to be instantiated. So it's been instantiated here, again, because a universally quantified statement can be instantiated with any letter you want, any constant, any variable, even ones that already appear in the proof. It's being instantiated with that new constant we introduced, A. So we have if PA and IA, then A is identical to S. So if you look at the relationship between lines 7 and 8 now, what's happened is that we've dropped the universal quantifier and we've replaced all of the X's with lowercase constants A's. Line 9 is just the simplification of line 5 being that string of conjuncts PA and IA and not LA. So we've dropped the not LA and we just have PA and IA on its own line. Strictly speaking, that should have been in parentheses, but your textbook kind of glossed over that when talking about identity statements. Because I think you can see from the translations, whenever you're working with predicate and logic statements with identity, oftentimes you get long strings of conjuncts, and it's tedious, frankly, to put parentheses around all of them. So sometimes the parentheses are dropped in these long strings of conjuncts like this, and that's what your textbook author has done. And it's what I've done here. So on line 9, we get PA and IA. And I think if you look at the relationship between 8 and 9 now, that should be pretty clear. Line 8 just says, well, if you have PA and IA, you get A is identical to S. So on line 10, which I'm highlighting with an arrow now, we get A is identical to S by modus ponens from line 8 and 9. Our initial assumption, line 4, was that C is identical to S. Line 11 just reverses the order of that using the identity rule, the second version of the identity rule. If C is identical to S, then obviously S is identical to C. That's what's going on here in line 11. Now, I want you to look now at the relationship between lines 10, 11, and 12. If A is identical to S, that's what line 10 says, and S is identical to C, that's what line 11 says, then according to the identity rule, A is also identical to C, and that's what's going on here in line 12. From lines 10 and 11, we know that A has to be identical to C. Line 13 is also a commutativity step from line 5 to get not LA on the left side of that string of conjuncts. So it can be simplified out on the next line, line 14, to get not LA on its own line. And obviously, if A is not an L and A is identical to C, then according to the identity rule, we know that C is not an L, because if A is identical to C, we can rewrite line 14, replacing A with the lowercase constant c. Line 16 just reverses the order of the conjunction way back on line 2, according to commutativity, to give us LC and PC. Line 17 is just a simplification of that to get LC on its own line. And now, once we have LC and we have not LC, that would be on line 17 and line 15. We can conjoin those together to get an explicit contradiction. C is an L and C is not an L. Some statement and its negation. That's what you see here on line 18. And that's how we're going to conclude our indirect proof. We started out way back. In fact, I'll use a different color here. Way back here on line 4. We started out by assuming C is identical to S. Later in the proof, which I'm going to use an arrow here to show, green arrow, we've shown that that leads to an explicit contradiction, some statement and its negation conjoined together, which means that our initial assumption has to be false. So we close off our indirect proof sequence. That's what's happening with that horizontal line right here between lines 18 and 19. And we've shown that our initial assumption is false. If our initial assumption was that C is identical to S, then our conclusion is going to be that C is not identical to S, the identity sign with a slash mark through it. And that's going to follow from lines 4 through 18 by indirect proof. And we are done. So I want you to spend some time looking at these two examples, both of which can be found inside your textbook. Look at the use of identity statements, and you'll see in both of these proofs that all three versions of the identity rule have been used inside these two proofs. This should give you everything you need to dive into the proof exercises in the second part of this week's homework. This is going to be by far the most challenging homework you've had to do all semester, which makes sense because it's the last homework assignment of the semester. So spend lots of time on it. This video hopefully shouldn't have taken you too long to go through. Like I said, there's really no mechanical way, a purely mechanical way to go through all those translations. So spend a lot of time looking through the different examples of the given statements and their translations inside the textbook chapter. Watch this video slowly, pause when you need to, look at the translations I've done. Same thing with the proofs. Get a hold of all three versions of the identity rule and look at both of these example proofs and see how the identity rule is used in the context of these proofs. And you should be able to plow through the proof exercises for this homework. As always, let me know if you have any questions or concerns. Let me know if you get stuck anywhere in your homework. I'm always happy to jump on Zoom or a telephone call with you and get you unstuck if you're stuck anywhere. Other than that, I hope you guys have a great week, and I will post a subsequent video next week to talk about how we're going to handle the last week of the course. Thanks again for all your hard work, and I will see you in next week's video.